second webinar. Yes, today we invite Dr. Ronny Hänsch, DLR. He's working at DLR and he's a very active scientist in the remote sensing society. One of his major is like pattern recognition or computer vision like that. So fusing satellite SAR images and optical images like that. So please refer to his background. And okay, Ronny, please start your presentation to save the time.
All right. Thank you, Junichi. Let me just pull up my slides. Right, here we go. Okay, so yeah, thanks for this nice introduction, and welcome everybody to this webinar. We have more than 100 speakers, and I just not speakers, participants, and I just had a quick look into who is here and got a little bit scared because I saw a lot of people that I know very well who are working since years on SAR and focusing on SAR. And then, I come up with the title of my talk that is like this: what SAR can learn from optical data, which is might be a little bit outrageous for some of you, but I hope you can bear with me. Just to take the most important message at the beginning, I'm by far not against SAR, right? I'm working for the Radar and Microwave Institute at the DLR, so this is my main job. But still, I think we can all agree that there are complementary informations in both the sensors, and this is what I want to talk about a little bit today. So this is probably something I can keep very, very short. This is why we love SAR, right? Why we think SAR is a very useful sensor. The most important property is we don't care about rain. We don't care much about cloud. We don't care whether it's day or night. We always get our images until we screw up the processing. But other than that, it's no problem. We don't have issues with clouds like an optical sensor would have, or in the northern part of very north or very south, mostly very north. In the south, there's not so much to see. You have problems of light half of the year, right, due to the Arctic winter, where optical sensors, they can still make images, but they look, first of all, very differently from summer, alone due to light conditions. And the noise goes also very high. For SAR, we don't really mind. No, it's always basically the same. And then SAR has this very nice properties that are making it complementary to optical images. We can penetrate vegetation to some extent, but also soil and ice, basically everything that is dry, we can penetrate. We not really measuring angles like an optical sensor would. We are measuring distances, we're measuring geometry and roughness of the surface. And then, of course, we have all those more advanced technologies with SAR that are in SAR, for example, for surface deformations or surface height, and pulsar, tomosar, and so on. And so we really like SAR. It's a very strong sensor, in particular if the images look like this on the right-hand side, which is an image from Munich. However, in practical applications, the data we need to deal with very often looks like this. So I don't know how many of you immediately recognize what this image is showing. It's just a small part of a much bigger image. And those of you who immediately see what that is, how much training went into your education so that you're able to do that, right? So for those of you who don't see it, we have a really tall building over here. And actually I have an optical image that is more or less matching, right? So this roundabout over here is what you see here, and this tall building that you have here, you see here. So for SAR, it comes a little bit with a cost, right? So the data processing is quite complex. It's usually a very long pipeline. We have different pipelines for different sensors, different pipelines for different final data products. That's a little bit different with optical imagery, although of course also there the pipelines are very complex, but they're a little bit more standardized. We have speckle, so strong random fluctuations that are making the manual, but also the automatic analysis of the data very complicated. We have geometric distortions, like this building is falling towards the sensor. So if you're not really educated in SAR, you might think that you see here the southern part of the building, so basically this part. But what you actually see is the northern part, right? Because the sensor is over here, it's falling towards this, as a layover is falling towards the sensor, right? So this is this part facing the roundabout. So the interpretation of SAR is also getting harder. And all of this together has a very tremendous impact on analyzing this data, processing this data automatically with machine learning, or in particular with deep learning, because here, most of the methods that we are working with coming from computer vision, so they were originally designed and tailored towards RGB images or maybe grayscale images, but certainly not radar images. At the beginning of deep learning for radar processing, what people usually did was they tried to, push data into the format the method would expect, instead of adapting the method. And only now, slowly, we are going away from this. But all of this together usually has this effect that a person that loves SAR is not liking very much. So if you compare the same model trained on very similar data, but one time on optical data and one time on SAR data for general purpose things like land use, land cover, classification, maybe building footprint detection and things like this, usually the optical data works so much better than SAR. It's of course different when we go into the direction of maybe forest height estimation, soil moisture estimation. So applications that are very specific to SAR, then of course most of that you can't do with optical anyway. But if you go to general image understanding tasks, usually it works better with optical data. Resolution is sometimes a little better. You don't have speckle. So I don't like to call speckle noise, but let's say the signal to noise ratio is a little bit better. And the analysis is just much easier, and the models are working with the data they were mostly developed for. So the advantage for SAR for those type of applications, it's not really that you get better results. The advantage is rather that you always got those results. While for optical images, you might not get the image, and then you don't get a result, even if in theory it would have been better. But this kind of like motivated me to look a little bit into approaches where we can leverage the fact that in remote sensing, we have those different sensors, right? We're not living in a world where we only have SAR. We are living in a world where we have different sensors, including optical and SAR satellites or airborne systems. So of course, I'm by far not the only one who is working in that direction. Actually, lots of the people here in the audience, I do know that you have similar works going on. So please don't expect me to cover just like everything that is over there. And of course, what I will do is focusing a little bit on work that I did together with students of me in the past. And I want to focus on three different ways how we can leverage optical data to improve the analysis of radar images. So the goal is not data fusion. Let me be very clear with this. So I'm not advocating that we should combine the modalities of different sensors during inference time. So the only thing what I want to talk today is that we can leverage the existing of different sensors during training time, but then inference is always based on SAR, right? So what I want to do is I want to have a good model that, provided with a radar image, gives me a good result. Today, it's all about semantic segmentation, mostly then to use land cover classification, but you can make similar stuff for other applications too. But it's always coming from a radar image, and the optical data is only used during training. Right. By the way, I see a lot of activity in the chat. I'm not jumping back and forth from chat to my talk. There will be enough time at the end to address your questions if there are any. But feel free to put it into the chat and then we can look at this later on. All right, so let's start with the first one. Pre-training with optical data, in particular transcoding. So the overall task, what we want to solve is we have a radar image. We have a little bit of training samples, not so much usually, because labeling radar images or remote sensing image in general is quite costly and difficult. And what we want to do is we want to train a model on this, both things together, right, with this as the input and this as the reference data, so that it's producing those semantic maps. So in this case, it's urban area in red, grassland or agriculture area is in yellow, water is in blue, and so on. So you can easily do that. We are doing this since years. You can do this with the shallow machine learning method. I'm a big fan of random forests. So the green bar here, this is a random forest approach. And the blue and the violet one, this is two different types of architectures for a deep learning model. And on the x-axis, you have the amount of training data that we used, only a very small part or all of this, and the achieved accuracy. And what you see is it's quite typical for this kind of approach. The more data you have, the better the things are. Interestingly, although not the topic of the talk today is, if you don't have so much data, training a deep neural network from scratch is actually not that good. No? So the shallow classifier is outperforming it by quite a margin. And even if you have a modern shallow classifier, it can hold up quite well, even if you have more training data. But then, of course, the deep learning approaches are, catching up and eventually surpassing the shallow method. All right, so in the idea, what we had here, what we wanted to do is we wanted to train a model, in particular a generative adversarial network, that is taking a radar image and is producing an optical image, a lookalike optical image, not a real one, just a synthetic one. So we have this GAN here in the center that we train with radar images, Sentinel-1 in this case, and Sentinel-2 images. And the only task this model has is, if I present you with this Sentinel-1 image, produce something that looks like the multispectral image. So this is quite a hard task because, as we know, SAR and optical images are showing quite different things. No? So it's not a simple lookup table that you can produce. If you see double bounds in a radar image, then put a red pixel there or something like this. That doesn't really work. What the GAN needs to do is it needs to implicitly recognize how does an urban area look like in the radar image? How does a forest look like in the radar image? And only then it can synthesize the texture of this area. So this means without explicitly telling it, this is a forest, and this is water, and this is field, and this is an urban area, it will learn to distinguish between those things because otherwise it can't solve this task of transcoding. So here you see a couple of those results. So this would be the input the input radar image. This would be the actual optical image. You see a cloud here, for example, and this would be the fake, the synthetic data that this again is producing. As you can see, it works rather well, right? So the major structures are there. It's not doing everything correctly, right? For example, this very small dirt path here, this road, that it's completely gone, right? And it's mostly gone because it's barely visible in the radar image. Here's an urban area. The GAN recognized it as an urban area, but put a road network there that is completely different because it's not really visible in the radar image, so it's just hallucinating that. But in general, it's get it right. No, where there's supposed to be a forest, there's a forest. Where there's supposed to be an urban area, there is an urban area. Now, I would be very, very careful of using those fake optical images. I've seen lots of people doing that. I'm usually strongly advocating against this because this is not an optical image. It just looks like one. And again, it's hallucinating stuff, whatever it can't estimate from the data. And it's very hard to distinguish, what is hallucinated and what is actually there and what might not have been possible to reconstruct. So what we did in this work was not using those optical images, those fake optical images. What we did is we used part of this GAN, in particular the feature extraction part of the GAN, and we put those features into a new network, just attached a small network for the semantic segmentation. This network is much, much smaller, so it does not need so much data in order to be trained. So this means we get away with a much, much smaller training database and still get quite reasonable results. So you could do this without a GAN. You could do this with a regression network. And in a few minutes, I will show you results for this. But if you do that, then basically the synthetic images look like that. But the main part is still there. You can recognize forest and so on, but it looks very, very blurry. No? There's not so much texture over there. So this is why we are using a GAN, where you have this generator that eats an radar tile, right? Then there are a couple of operation layers, mostly downsampling and convolutional layer, a couple of other things. Then we have this upsampling pass that is then producing this transcoded fake optical tile. And this one is fed into the discriminator, and the whole job of the discriminator network is to say, well, this is a real image, or this is one image that was generated by the generator. And then you train this whole thing end to end. In particular, you play those two networks against each other, and this is how you train it. It's very painful to train again. It's not really converging. It's oscillating a lot. You don't really know when to stop. But with a little bit trial and error, you can actually make this work. And then if you do this, you go from this results, which is only using a regression loss, so just like mean squared error. Here we use the adversarial loss. So you get much more texture. It looks much more real, but of course, lots of this texture is just hallucinated. No, it's not really there. It's just plausible. It's plausible that it would look like this, but it might not really be correct. All right. But as I said, we don't really care about those optical images that we produced. What we want to do is to classify this data now. So what we do is we just add the classification branch, or semantic segmentation branch, to this generator that is using those features that have been learned and trained on this transcoding task. And then we only need to train this small network. There are a couple of options what you can do. For example, you could just train this last block, or you can train the whole thing from scratch. Both is possible, and we tried both. At the end, it doesn't matter too much. And this is the results we get. So in green is again the random forest, blue and violet are the two networks that are very alike to the generator, but they were trained from scratch. And then in orange and red are the results for this network that has been pre-trained on the task of transcoding. And what you can see, it's not just kind of consistently outperforming all the other methods by quite a margin, actually. It also stays more or less constant with respect to the training data size. So even for a very, very small data set, where training a network from scratch was worse than a shallow learner, we still get really, really good results because the classification network is so small. So even this very small training data set is enough. So this works quite well. Just some qualitative results. So this would be the input SAR image. This is the optical image that's not used during inference. This is just for your reference. This would be the reference map, so the target. This would be the network when we train it from scratch, either with only a very small training data set or with all the samples that we have. You will see, well, the major stuff is there, but results are quite bad, actually, in particular if you don't have much data. And this would be if you use this transcoding-based pre-training, where we either, again, use a small training data set or all of the samples, and you see the results are quite stable and quite good as well. So this works quite well, but the disadvantage is really that you need to use this GAN, right? This generative adversarial network, where you feed your input image into the generator that is producing a synthetic image, and then either you feed the synthetic image or a real optical image into the discriminator, and then the discriminator needs to decide whether it's real or synthetic, and then you train both together. It's a very nice idea, but it's very fragile. Very hard to train as well. So we, in a follow-up study, we ask ourselves, okay, what would happen if you just make it simpler? We don't have a GAN, so we don't have this adversarial part. We just have regression networks, super simple to set up. It's just a unit, the SAR image goes in, we train it with the corresponding optical image, and it's supposed to result to reproduce this. Or the other version, we make it even more complicated, and we use the cyclic GAN, where this synthetic image is put into another generator that is now generating a SAR image based on an optical image. And then the synthetic SAR image is compared to the original SAR image, and then you have an additional loss. So here it's getting even more complicated because now you have two GANs with one generator and one discriminator each, and you need to train all of them against each other. So it's even more complicated to train it. Here you see some qualitative results. So this would be the input SAR image. Again, it's Sentinel-1. This would be the regression network. You see it's getting the stuff more or less correctly, but it's very blurry. With a GAN, you get much more texture and contrast into it. Cycle GAN basically didn't work. Despite all of our efforts, we never really got it to produce good results. And this would be the reference optical image. Again, we don't care about those optical images, those synthetic optical images. We just throw them away afterwards. It's really just to train the network, right? To pre-train the network. And this would be the results we get. Again, on the x-axis, you have the number of training samples. In blue, the blue bars would be if you only use a SAR image and train the network from scratch, the more data you have, the better it gets, right? It saturates at some point. And then any kind of pre-training based on this transcoding works better. Even with a cycle GAN that produce quite bad visual results, still gives you a performance gain. The GAN, what we already knew, works really, really nice, gives you perfect result. But interestingly, if you just do a regression network, you still get a really good performance. It's slightly worse than getting, training with a GAN, but only slightly. And I would argue this small decrease in performance might be versus to not have this hassle to train a generative adversarial network. So yeah, if you have data, optical and radar data, this is an approach that I have found works very, very well. All right, the second approach I want to talk about is a little bit differently. So also here you need to have aligned optical and radar data, but the idea is more that we assume we have a model, a neural network that has been trained on optical data. So it can again be a unit, but can also be other networks, doesn't really matter too much. You put optical data in, you train it with whatever you want to predict. So here we used SpaceNet 6. Where it's building detection, building footprint extraction. So you train this optical network, or you already have it in the standard way. But now we don't really want to have an optical network. We want to have a radar network, right? We want to have a network that is getting a SAR image and is producing the semantic maps. And the idea here is that we leverage this optical network because we have seen before that optical networks for this type of task at least are usually solving it much, much better. So the idea would be a little bit, can we kind of, although the new network gets radar data, can we kind of match the statistics of this optical network? So what you could do trivially, you could have a radar network use again, or a regression network to produce optical data as in the work before, and then feed it in here and just use this optical network. But this is quite dangerous, as I said before, because if you just use the regression network, then the quality is quite bad from the optical image. Also, the statistics are quite bad, so this would probably not work. And if you use again, there's a lot of hallucinated details where the network would give you an estimation, but it would be most likely wrong. So instead, what we wanted to do is we have a new network that is only there for the radar data, right? It gets the radar data, and it's not trained on any kind of output masks, but it's trained instead of matching the features that the optical network has computed. We trained different configurations, so you can try to match only the output features, or you can train to match also some intermediate features, or maybe multiple features at different positions of the network. The last one works the best, right? But the core principle here is really that you have a radar network that is getting the radar images, and it's trained not by like a cross-entropy loss based on the semantic maps, but on a regression loss to reconstruct the features that the optical network has been computed over an image that is co-located with the SAR image in time and space. And then optionally, what you can do is take this radar network and fine-tune it on the data that you might have, right? And then you just do the normal cross-entropy loss on your semantic maps just to fine-tune it a little bit. We tested this on SpaceNet 6, as I said, with different architectures. Here I only have 3 of them, the unit with a WG19 backbone, a unit with an ExceptionNet backbone, and a deep level v3 with a Resonant 50 backbone. So this would be the results when we train it on the optical network, right? So this is basically the result of this network over here. And the red bar is the results when you get when you train a radar network from scratch without anything. And as before, we see, well, the radar network is much worse than the optical network. Now, this is what happens when we do the feature reconstruction. So we only train the radar network to match the features of the optical network. And it's not always working that good, right? So here we actually lose performance a little bit. Here we are more or less on par, but for the smaller network, we gain a little bit of performance. But just to be clear, actually, I already like this results a bit because this network has never been trained on training data with radar data, right? It has never seen a combination of radar image and building footprints. It only has seen radar images and the corresponding features computed from an optical image. And still, although it has never been really trained on reconstructing footprints from radar imagery, and extracting footprints from radar images and optical images is a very different task. You already gain a little bit something for some of the architectures. But then if you go ahead and you use this network and you fine-tune it a little better on the data that you might have, you actually get quite a performance gain. So here it's quite significant. So we go from I don't know what this is, 25%, 23% to more than 40%. Even in this case here, where the radar network was already quite strong, we still get a little bit of a performance gain, and also here. And this is something we saw through all the different architectures we have tried. The performance gains are sometimes small, sometimes large, but they are always there when you do this. So basically, all what you need here is a network that has been trained on optical data for the task you're interested in, and then aligned optical and radar images so you can do the feature reconstruction, and maybe a little bit of a fine-tuning data set. All right, and I hope I'm not too fast, but this already brings me to my last method I wanted to talk about, where again we want to use coexisting optical and radar images, this time in a self-supervised learning framework. In particular, we used Dino, which is a very common and standard approach, already a couple of years old. And the basic idea is that you start with your input patch, your input sample. So in this case, it was again a radar image. You produce two different views of this. So usually what you do here is certain geometric or radiometric transformations. So for example, you can zoom in a little bit, or you can maybe translate or rotate a little bit, something like this. And the idea is now that since these are just two different views of the same sample, when we put this into a feature extraction network, the corresponding features should be the same, right? Because they're coming from the same sample, so the difference should be small. The problem with this very naive approach is that there's a trivial solution to that, right? The encoder might learn, I just map everything to 0. Then you always have perfect consistency between the different features, but it's a very useless network because it's always extracting the same description for everything it sees. Other approaches use negative examples for that, right? So that you want to have, okay, I want to have that for the matching samples, I want to have the distance of 0, but for a negative example that is not the same thing, I want to have a big distance. No? So then if the encoder would map everything to the same value, which is called mode collapse, that wouldn't work in this constant. But you have this disadvantage of using negative examples. So Dino is solving this a little bit differently by having the encoder shared between the two views. This one on top here is trained by common backpropagation based on the loss that this one should equal to this one, basically. But the network down here is basically a running average of the network on top over here, and it's not trained. So this means this mode collapse is a little bit avoided. And then the idea is, once this is trained, for this you only need data, right? So there's no reference data or ground truth or whatsoever, right? You only need data. And then you use this encoder that you have trained, you plug in on top of it a new network, a decoder that is solving whatever task you're interested in. So in this case, we wanted to have a land cover map. So basically, you're building a unit again where the encoder part of the unit was pre-trained by this self-supervised technique. And then again, since now you only need to train the decoder or maybe just fine-tune the encoder a little bit, you get away with a much smaller data set than what you would have needed when you train everything from scratch. And now the idea we had here a few years back was that when we are generating those different views, what we can actually do is to use an optical image, right? So you can still do some kind of transformations, like zoom in a little bit, translate a bit, rotate a little bit, but you don't do this with the radar tile. You do this with the corresponding optical tile. So in this case, we used Sentinel-2. Still did a geometric transformation on that, and now we say, well, in principle, this encoder is supposed to construct features that are very informative for a semantic task, right? For semantic segmentation. And that means since the radar image and the optical image shows the same semantic content, those features should be close to each other, right? Of course, you see very, very different things and the same thing in a different way in an optical image and in a radar image. But if you look at it from a semantic perspective, from the classes that are present, it should be the same, right? The features should not be so different because at the end of the day, they are showing the same scene and there is the same semantic classes present, like forest area, grassland, water, and so on. So this is the idea that behind of forcing the network to compute features that are robust towards whether an optical or radar image is put into the encoder. But the remaining of the idea stays the same, right? Then this encoder is used in your downstream task, and you only train the decoder. So here for the evaluation, we used data fusion contest from 2020 that was giving us exactly this. We forgot about the low resolution labels, only used the high resolution labels, and then the Sentinel-2 and Sentinel-1 imagery. So here you see a couple of results. This one here would be the radar image. This would be the corresponding label of the data fusion contest, so the reference data for the different classes. And here you see the result if you just use a random initialization. So you don't do this kind of pre-training. You start with this network, it's randomly initialized, and you train it from scratch. So what you see is it works, right? You do get results. In particular, water is easily recognized, but finer structures are not there, right? So the network gets the main idea, but it's not really doing a really good reconstruction of the actual semantic content. So the average performance is around 34% in accuracy. And here you see the accuracy over the different classes. Water is really easy to do, but for the rest, it struggles a bit. These are the results when we pre-train it on ImageNet. ImageNet is a very common and standard data set that made deep learning famous. Basically, there it was also started. But of course, it's close range images, RGB, very tiny. So it's very, very differently from what we are feeding the network here, actually. So you don't gain really much. You do gain a little bit on average, but most of the classes are losing quite a bit. Others win a little bit. So pre-training on ImageNet, it helps a little bit on average, but not really. This is when we do the pre-training on SAR data only. So we are not using the optical data. We're only using different augmentations of the SAR images. And now results are getting much better, right? So comparing the 34% on average accuracy with the 41% we are having now, this is quite a leap. So the network starts to pick up on details. Classes that were missing before are more present now. And those are the results when we use also additionally the optical data as an additional view to during the dyno pre-training. And then all the classes gain a little bit something compared to the baseline. And again, compared to only training on SAR, we again win a little bit. It's not too much, but I mean 1.5 percentage points. It's actually not too bad if you have data that is existing anyways. Some more numbers just visually presented. So this on the x-axis is again the number of training samples that we have. You see, I really like this type of graph because it shows very nicely where you get benefits and at which point you just have enough data and you don't need to do pre-training anymore. And then the red bar would be we train it from scratch. The blue bar is we train it on ImageNet. Green is we train it only on radar images, and orange means we train it additionally also on optical images. And what you can see, well, ImageNet pre-training helps a little bit, right? Although it's so different from SAR, but in particular, if you have not so much data around, then any kind of pre-training basically helps. At least the network can get the very basic stuff like edges are important, blobs are important, and stuff like this. It can get from the pre-training on ImageNet. But where you really get a boost if you do something that is reasonable for SAR, either using dyno on SAR data only or together with the optical data. Then you get quite some boost and also quite consistent with a little bit fluctuations here and there, but otherwise quite consistent across all the number of training samples that we used. All right, and that is already the end of my talk. I see I could have gone a little bit slower. I hope I didn't lose you, but this means we have a lot of time to address any kind of questions that you might have.
Ronny, thank you for your excellent presentations. So for participants, now it's time to start the discussions. If you have questions or comments, please write into the chat box. Yes, and Lakshmi, if there is a comment or questions, can you read it out? And maybe you are better than than none.
Thank you so much, Professor. I will try to read it. So I'm going to read the questions from Q&A section. So the first question looks more as a curiosity. I'm not sure, but I'm going to read it. So it is from Anirban. It says, Dr. Hans, as Pulsar, I think this is the data from JAXA, LS Pulsar, data are going to be expired. So I'm not sure if the person is asking or commenting. Do you have any thoughts on this?
Maybe that was a confusion. So I didn't say pulsar, so not PAL SAR, but POLSAR. So POL standing for polarimetric SAR. So it's a specific mode of SAR. In none of the methods I've shown here, I have used pulsar data. It's always POLSAR data.
Thank you. So the next question says, which data are to be uploaded to GEE data catalog? Could you shed any light on that?
It's the same person who asked the previous question, so I guess they are connected. And no, I don't have no knowledge of pulsar.
Thank you on that. So maybe Anirban can clarify more on the question. So another question is from Jonathan. It says, thanks for this excellent presentation. What is the scope and applicability of deep learning to estimate Sentinel-2 using radar data? That is it possible to use these S2 estimates for Earth observation applications, or is it not yet possible?
Yeah, that's a very sensitive question. Thanks, Jonathan, to bring it up. You need to be very, very careful. The problem is, yes, you can synthesize optical imagery from radar. I've shown a couple of examples in those slides, and there are many other papers out there that are doing that. And it's very, very tempting to do this because optical data has, for example, the issue of clouds. Radar data looks through the clouds. So we could say, hey, let's use the radar data to synthesize what should have been there in the optical data and get rid of all the clouds in our optical data. It's very, very tempting to do this. If you're doing this with any kind of network, you still need to be aware of that there's no magic happening. Any kind of information that is not present in SAR, or the network doesn't have the capacity to estimate from SAR, can't be present in the synthesized optical data. It's simply not possible. Where should it come from? So this means, for example, if there's in a flower field, right, and the flowers have red blossoms, you can't get this information from a radar image, right? It's not possible. So what a network might do is to put the most likely outcome there, right? So maybe an average color, which would still be wrong. Or if you use something like again, it would put a plausible color there and might be blue instead of red. I brought this example up before with the road network. The GAN recognized this is an urban area. Urban areas have roads, so I need to synthesize a texture in the optical image that has roads. So it put a road network there. But this road network has nothing to do with the actual roads on the ground. Now, if you say on top of that, now I train a road network extraction model that is, extracting the road network, it would do that, but the road network would be completely wrong, right? It has nothing to do with what is seen on the ground because you don't really see the road network in urban areas in Sentinel-1. So in the best case, what you get there is something that is not doable, and you can recognize it's not doable, or you get something, if the GAN is really good and it fakes something very, very realistically, you don't even know that it's fake. You don't even know that it's wrong. So it's very, very dangerous. My recommendation is don't, or if you really want to do, have some kind of grounding, right? So you need to ground the synthetic images in another source of data. So for example, you could use different time steps, right? Where you say, okay, this is not the optical images from this time where I have the cloud, but maybe it's, a couple of days earlier or later, but so the information is not the same, but I can use this information in order to ground whatever the synthetic data is doing there. But still, I would be very, very dangerous, very, very careful, because I think it's very dangerous to just neglect those risks. Still, there are a lot of very interesting works out there. Some of them are addressing this, others just are ignoring it, and that is a dangerous path. And another recommendation is, if you really want to work in this direction, test your downstream tasks, right? So you're trying to synthesize optical images for some reason, right? You want to use this somehow. Maybe you want to compute vegetation indexes that are not really possible to be computed from radar images, or other kind of indices. Or maybe you want to have, an optical network that can then be applied to detect whatever you want in your Sentinel-2 imagery. Test those downstream tasks. Don't just look at the images and say the images look nice, right? They always look nice if you use the right network. Evaluate those images on your downstream task, whether you really get the performance in those areas that you expect. And if not, you have an issue, right? No matter how beautiful your images are looking like. And I also recommend, if you're a reviewer, to look out for this kind of stuff in the papers that you're reviewing.
So thank you so much. Another question from, I think it's from anonymous attendee. It says, what are typical concrete use cases where this line of work can be useful?
Yeah, a good question. A very critical question, and it's funny that it's coming anonymously. So typical use cases where you want to have something like this. So all I have talked about was with the goal in mind to make networks on radar images stronger, right? To give you a better performance for radar imagery, automatically detecting whatever you want. So basically, your question boils down to, what are use cases where radar data is useful, with the constraint, though, that also optical data needs to be useful, right? Because if you talk about soil moisture estimation, which is difficult from optical data, and then of course, leveraging optical data won't help you much. But if you talk about things like land use, land cover mapping, building footprint extraction, flood detection, where radar data is really important, wildfire detection or monitoring, this kind of things, I think those would be use cases where it's paramount to have strong networks that can work on SAR data, because for floods, for example, optical data is difficult. Optical data might be occluded by clouds, and then it's not useful. You can't get it during the night, also not useful. So for this kind of applications where you're relying on very time-sensitive information, right? You want to get the first image that is available, and if it is a radar image, and it's quite likely it is one, then you want to be able to use it as good as possible. And in those use cases, I think those approaches would be helpful.
Thank you so much. So another question is, I think it's from Olivier, and it says, can you give us best practices and tips to align, that is to co-register Sentinel-1 and Sentinel-2, especially since SAR is side-looking?
Yeah, also an excellent question, because for all of those approaches, we need to have aligned data. I would say for most of the more mature satellites, the geocoding already works quite well, at least in easy terrain, right? If you have like strong mountains, you might have an issue, but otherwise it should be more or less okay. It's not really my area of expertise, though. You might have noticed all the data I've used here is benchmark data, where this was already done for me. The only thing I can say is that in particular, if you have again, it's really important that it's correctly aligned, because otherwise, the discriminator sees the SAR image and the optical image together, and then is supposed to say whether the optical image is fake or not. Now, if it's synthesized, it's perfectly aligned, right? Because you're taking a radar pixel and you produce an optical pixel, so it's perfectly aligned. And if the data is not perfectly or sufficiently aligned for the real case, for the real data, then the discriminator has a really easy time to distinguish between the two. It's aligned, fake. It's not aligned, real. So it won't learn anything useful. And then basically the adversarial loss is meaningless to train the generator, and you're back to regression. So there, it's very important to have that. Since you're talking about SAR side looking, don't try to align building facades. Simply different data, right? You can't do this. So the only thing you can really robustly align is flat surfaces, no? But the roofs you might be able to align if you want, but then all the building facades are gone in SAR. Maybe you don't want that because they're meaningful. So yeah, it's a very difficult topic, and I don't have too much insight in this, unfortunately. What I can tell you is you can watch out for the SpaceNet 9 challenge. So the image you're seeing right now was from SpaceNet 6. SpaceNet is a consortium of different institutions that are bringing out benchmark data sets and new challenges every once in a while, mostly focusing on buildings and road extraction. And SpaceNet 9 will be for the alignment of SAR and optical data, in particularly Maxa data, so worldview for the optical one, and Umbra for SAR in over dense urban areas, actually. So looking out for that and looking what the outcome is might give you some further insights.
Yes, so the next question says, it's by Yasumin. It says, thank you for your presentation. How can the integration of SAR and optical data address the limitations inherent in each modality, leading to more robust and accurate remote sensing applications?
So this is a question that goes a little bit beyond the scope of the talk today, because none of the approaches I showed you today is doing data fusion, right? So the different modalities are not integrated. We always work on the radar images at the end, right? So the input during inference time is always just the SAR image and nothing else. We are just leveraging the optical data during training in order to produce a stronger signal during training, helping the radar network to learn things it might also have learned from scratch, but just with much more data available. So the approaches from today can't really address this. So now when we are talking about cross-modal learning or something like this, I don't really think you can learn something that is not there in your data, right? So whenever you use only one modality, no matter which one, during inference, what is not there can't be estimated. Even if you're training it on another modality, it doesn't really matter. If it's not there, can't be estimated. The only chance that you have is doing data fusion, which usually works quite well. So usually for data fusion, for many applications, the results get better than compared to only using one of the modalities. So even the optical data, the optical network gets usually a little bit better when it has also access to SAR images in parallel. Because then if you have this complementary information, so a part of your signal that is not there in the other modality, and you have the modality there present, then you have a chance to do that if you do it in a meaningful way. So data fusion is really a nice way to address this, but it comes of course with the cost that if your sensor has limitations, like for example, optical data might not always be available, might be occluded by clouds, you bring those limitations into your data fusion approach as well, right? So any kind of constraint that your data has or your sensor has, right, it's just multiplying when you do data fusion. So if you have 4 sensors, right, each of them maybe have only one constraint or one limitation, but in your data fusion approach, suddenly you have 4 limitations.
So I think there is another question that you might have touched a bit. I think it's about, so any thoughts on using it should be, I think, interferometric, but I think it's interferometric coherence as well as single scene data.
Lots of thoughts, yes. Yeah, so today we only used pulsar data, right? So single scene data as you call it. INSAR is of course very relevant. I don't think so much for land use, land cover mapping or building footprint extraction, probably not. But for other things, yes, of course. Whether it really aligns with optical data depends on your application, right? On your downstream task. and also a little bit how you exploit this. So I've seen works on forest height estimation, for example. It's one of my PhD thesis is working on that. And he did experiment with including optical data together with coherence in order to do forest height. And it does help a little bit, the network to get some parameters correctly that it would not have got correctly by coherence alone. So I think it's an interesting way forward. But I would say it depends a lot on your downstream application, whether this is, meaningful or not.
There's a long question from Sylvia. It says, thank you very much for the interesting presentation. I have a question regarding the relevance of the alignment of SAR and optical data in the context of pre-training by multimodal SSL. In several applications, I would like to analyze SAR images in the slant range. Have you tested if the Dino method is also successful with a pair of SAR images in slant range and optical images showing the same content, but in ground range? Are the different image dimensions problematic?
Yeah, let's start at the end. No, I didn't test that. Would be an interesting test though. The alignment is getting much harder then, of course, no? That being said, I think this is really a little bit a problem, applying deep learning to SAR imagery, because nowadays we need big data sets, and this means we don't sit down and label the radar images. We use existing labels. Maybe they are coming from optical data or from OpenStreetMap or whatever. And they are usually in geo coordinates. And so far, most of the people, there are few exceptions, but the vast majority of the people, including myself, are not saying, let's project this reference data into slant range. Instead, what we are doing is we are projecting, slant range into ground range, and then, the stuff is more or less aligned, and then we can train our neural networks. So there's nothing too much wrong with this, but it's kind of violating this golden rule of SAR that you never geocode your SAR images, but you geocode the product, right? So we're working with the SAR data as much as we can. And that means slant range, and this means complex value data and so on. And then the final product we are mapping into world coordinates, into geo coordinates. Now for deep learning, nobody is basically doing that, apart from a very few exceptions. And I think this is a problem because this is limiting our methods by quite a bit. So yeah, it's a very valid question. I think we should go more into this direction of projecting the things we want to estimate into slant range and then work from there for training. Working directly with slant range and combining it with data in world coordinates is an interesting thought, though. I haven't tried it yet, and I'm skeptical whether the differences in the geometry are not too big in that. But no, I don't have practical experience on that. But good questions.
Sorry, please continue.
No.
So I think I'll take one question from the chat as it was asked before the Q&A one. So it's from Winhard. It says, hi, Ronny, nice presentation. What I have got from your presentation, it is not reliable and appropriate to only use SAR data for implementing ML and DL. Is it? I think it's a kind of question. So thanks. I'm Winhard from Indonesia.
Well, I wouldn't go that far. There are still lots of models and application where directly training on SAR is giving you very good results. It depends a little bit on the downstream task. Also, even for this type of task, like land use, land cover classification, you can build very strong networks that are only trained on SAR, that are giving you very good results. In particular, you can do self-supervised learning with radar data, right? I mean, like a masked autoencoder or something like this. It's a little bit more modern than Dino. It works quite well, even for SAR. No? So you can do that. It's not like this is a path you should not take. It's more like if you are lucky enough to have other modalities around that are, fitting nicely to your SAR data. For example, they are well spatially and temporally aligned. it's worth exploring to exploit that, to leverage this. And today I showed different ways to do that, but by far those are not the only ways. And then I think even a very good SAR network, excuse me, can still benefit from this. So it's not like it's not working at all if you don't do that. I think if you have a very strong SAR model, it works still quite well, but it will still probably benefit if you do something similar to that. No, you get another performance boost.
So I think he also has that question says, why don't you use Tandem X or TerraSAR X and use Sentinel instead? Is it because of the wavelength?
No, has nothing to do with the wavelength. There are barely any legal benchmark data sets for TerraSAR because legally it's very, very difficult to publish TerraSAR imagery. You can very easily get it as a scientist. You write a science proposal, you get the data and you can work on it, you can publish on it, you can publish your results, but you can't build a benchmark data set. No, you can't republish this data. That's a big issue with TerraSAR, which is very complicated, right? It's not helping science. It's going against reproducibility and so on. In particular for deep learning, where we need those big training data sets, it's very complicated, very critical, but it is what it is. So it's very complicated to publish TerraSAR data in a benchmark data sets, and that's why I'm not using it, because I want that my work is comparable to others, and that means I need to work on data that everybody can freely use, and that's just not the case with TerraSAR. That doesn't mean that those approaches are not applicable to TerraSAR. I mean, internally, we work with TerraSAR data a lot, and we apply those methods also to TerraSAR data, and it works. That's not a matter of the sensor, or it's not a matter of the wavelength whatsoever. It's just like there are barely any public benchmark data sets that are using TerraSAR or Tandem.
Lakshmi, it should be the last question.
Yeah, I think I'll just take two more questions, but there are still, I see 7 questions, because we try to limit it within 1 hour. So sorry for that, but I'm going to take this question by Luca. So maybe second last and then the other one. So Luca says, hi, Ronny, thank you for the interesting presentation. One of the main problems that I faced during multimodal analysis of multispectral and SAR images is the different acquisition geometry that is challenging problem to manage in urban scenarios. In your opinion, how is it possible to manage this problem?
Well, I don't think I really have a solution for you. So I think aligning is a very difficult task, because it's not just that the acquisition process is different, right? They are literally seeing different things. SAR is side looking, you see the facade. Optical is usually nadir looking, no? So you only see the rooftops, not the facades. So if you have two data, if you have two pictures, even if it would be 2 times optical data that are showing different things, you can't align it, right? You can make holes into one, or you can delete the facades in the other, but that's about it. So if you work in dense urban areas with high-rise buildings, you can't rely on the perfect alignments of these buildings. If you have flat surfaces, agriculture areas, water bodies, that is possible. Roughly via geocoding already, and then there's some fine-tuning possible. There are various approaches out there. But yeah, for anything that is elevated, you will have problems. There are things a little bit going in that direction. For example, you could try to estimate a height, like a height profile of your scene, and then use this information in order to align it in 3D. That has been done a little bit in the past, but I mean it's very complicated, no? And I'm not so sure whether it helps you so much. So the question is more, if you're in this situation that you need this very good alignment of things that are just not aligning, whether you're looking at your problem in the right way, or whether you should actually look for an approach that does not require this perfect alignment.
So thank you so much. Here is the last question by Sabun. Thank you very much for this amazing talk, Ronny. I'm just wondering if down the line we can come up with certain land cover types where generated synthetic optical data are more reliable, for example, water than others, for example, road, and then put some amount of confidence metric to land cover classes.
Yeah, sure. You can do this. No, for example, first of all, you could use more modern versions to synthesize data. So nowadays, probably nobody would use again anymore. You would use a diffusion model where the situation is already a little bit better. It's easier to train. It just takes more time, and results are usually better and a little bit more deterministic. And then, of course, what you can do is like an uncertainty quantification analysis on top of it. For example, a very easy thing to do is you could generate different variations of your input, same as you would do with data augmentation, and then shift everything through, and you see how the output is varying. And if it's not varying at all, no matter whether the image is rotated or mirrored, or you add a little bit of noise, your water body is always looking the same in the synthesized data. And that means it's kind of reliable, probably. But if the output is varying a lot, then it means it's not very stable, right? There's a lot of fluctuation going on there. So you can kind of quantify how certain your synthesis network is in the data it's synthesizing. And you can use this. That would be one approach. There are probably other ideas around this as well. But the thing is more that what do you do with this information? Can you really, if you have a downstream task where this data is then automatically analyzed, can you really exploit this uncertainty in a meaningful way other than just, well, there's a cloud, the radar network is not producing reliable results, so I can't delete the cloud. I think that would be the most common output probably. So I think what is more successful probably is this type of like visual grounding, that you have other data around that you can use to ground whatever you're synthesizing there, and then test it on a downstream application. That's very important.
So thank you so much. I'm sorry we had to stop this Q&A session now, as we're already 4 minutes beyond our specified time. But I think it was a great session with lots of questions. Thank you to Ronny. So I have posted the link for the future webinar organized by the same working group 3. And you can register. So these all are about active remote sensing. So active remote sensing. So maybe some of the questions that we are putting in Q&A session may be valid to some of our invited speakers in the future webinar series as well. So with this information, I think we had 146 participants actively involved until last of the presentation. So it was very nice. And now I would like to thank you everyone, Professor Junichi, Professor Ronny, and all the participants. So with this, over to you, Professor Junichi.
Okay, Ronny, thank you for your wonderful presentation. So for participants, as you know, today's video will be uploaded to the YouTube, I think. And if you have a chance, please look at it. And also, we, ISPRS Working Group 3x3, organize this webinar every second Wednesdays of each month. So please join the next webinar also. Okay, thank you for joining us. Now it's finished. Okay, bye-bye.